Let us continue with what are the types of hot rolled steel sections and what are their applications, practical applications, under what circumstances what section we have to provide so that it will behave most efficiently, effectively, so that we can make use of our material, okay, comfortably without any failure. So that is what the choosing of material, okay, choosing of section. So choosing of material is one thing, choosing of section for particular structure is also very important because sectional efficiency also plays a vital role. So what section we have to keep at what circumstances, that is a very important decision to be taken by the civil engineers when you go for typical construction of any structure. Now, what are the different types of hot rolled steel sections we are having? Let us look at that. So, types of hot rolled steel sections. Types of hot rolled steel sections. So, what are the different types of hot rolled steel sections we are having? Let us look at that. The first thing is Indian standard rolled steel I section. So, we have Indian standard rolled steel I section. The second one is Indian standard rolled steel channel section, and the third one is Indian standard rolled steel T sections, Indian standard rolled steel angle sections. The fifth one is Indian standard rolled steel hollow sections, Indian standard rolled steel flat sections, Indian standard rolled steel strip section, Indian standard rolled steel plates, Indian standard rolled steel sheets, Indian standard rolled steel bars. So these are the 10 types of sections which are actually produced from Indian rolling mills. Okay, hot rolled steel sections are classified into 10 types. What are those? I sections, channel sections, T sections, angle sections, hollow sections, flat sections, strip sections, plates, sheets, bars. So these are the 10 types of hot rolled steel sections which we are getting from Indian rolling mills. Fine. Now let us understand, dear students, these 10 types of sections are basically used for steel structures construction. Fine. Now, what are their applicabilities? Where I have to go for I section? What is the significance of I section? What are the benefits of I section? Under what circumstances I can choose I section as a steel member for construction? So let us look at that one by one, all these 10 types of sections. Some of them are extensively used for construction, some of them are very rarely used in construction. According to their performance, according to their stability, strength aspects, we will be choosing the appropriate element. Okay, fine. Now let us start with, so one of the question asked in other competitive exams also, hot rolled steel sections are classified into, what is the answer? 10. 10 is the answer, 10 types. Please understand that. Now let us see what are the, what is the I section, what is the importance of I section, let us see, then we go for the other sections as well. So first one we are talking about I section, Indian standard rolled steel I section. So, in case of I section, this is very important section it is, I section. The very important advantage of I section is that when I draw the I section, look at here carefully. So, when I draw the I section, so this is how, so there are two things which you have to understand basically. So, this is the theoretically we can have I section something like this. So, this is the flange, this is the another flange, and this is the web. These are the two flanges and the middle fellow is the web, okay. So, this is how people draw the I section generally on paper, okay. But the thing here is that this is not the section you can observe practically when you talk about the rolled steel I section. So, what happens in case of rolled steel I section is that we will be having this kind of processing, what we call as filleting. So, please try to understand this carefully. So, this is what it is. This is how actually rolled steel I section is manufactured from the steel plant. So, this process, see here, there is a lot of difference between this I section and this. Both are I sections only. Listen, these are what we call parallel flanges. These are the sloping flanges. Most of the time we will be having only sloping flanges for I section for practical considerations, because when I apply a load on this I section, look at here carefully. So, there is a flange of wider width available here, and when you come from flange to web, the thickness is drastically reduced. So, whenever I apply a load, the load is taken by the stronger element flange, then suddenly it is transferred to the web element. At the intersection we have stress concentration. There is a stress concentration happens when the load transfer from flange to web. These regions of intersection of flange and web are very critical. So, excess stress concentration leads to failure of this section. That is the biggest problem with this kind of I section. That is why what the people do is practically the stress concentration is eliminated by gradually reducing the dimensions. Here dimension is more, as you go down dimension keeps on decreasing. So, this is how the dimension gets decreased, then the stress concentration effect is eliminated here. But here the width is uniform, suddenly it is reduced, that is why stress concentration comes here. So, this process of providing gradual transition between flange to web, this process or this technique is basically called as the fillet. This is basically called as the fillet, okay, and this is also fillets bottom. So, this filleting, the process of introducing gradual transition between flange and web is called as the filleting. This is also a question asked in the GATE exam once, okay, please understand it. So, most of the rolled steel I sections are looks like this, but whenever I talk about board, when I talk about explanation of this section, I conveniently use this one because it is easy to draw here, that is why I can use that. Now, what is the advantage of I section? Let us look at that. The advantage of I section is that it is a symmetrical section. See here, what is the meaning of symmetrical section? See here, when I cut about, see here, exactly, I am cutting about YY, this is the YY axis, vertical axis is this, and this is horizontal axis is ZZ. ZZ is the horizontal axis, YY is the vertical axis. This is the YY is the vertical axis and ZZ is the horizontal axis. So, look at here carefully. In these two axes, which is called as major axis and which is called as minor axis, that is the question. Can you please tell me, out of these XX and YY, which is the major axis and which is the minor axis? So, this ZZ axis basically called as the major axis. This ZZ axis is the major axis and the YY axis is called as the minor axis. This is the minor axis, okay. So, understand dear students, why ZZ axis, horizontal axis is called as the major axis. Reason is very simple. The criteria for deciding major or minor axis is purely dependent of moment of inertia. So, I section is having larger moment of inertia about ZZ axis over the YY axis. Therefore, ZZ axis is called as the major axis, okay. That is the moment of inertia is the criteria. So, for an I section, IZZ is more than the IYY. So, therefore, we can say that ZZ axis is the major axis and YY axis is the minor, because it is having least moment of inertia. That's why it is called as minor axis. Now understand, dear friends, this particular section is symmetry about both the axes. What is the meaning of symmetry about both the axes? You cut about YY axis, you are able to divide this I section into two pieces, and which is one side is the mirror image of the other side. So now you take ZZ axis, cut about ZZ axis, then you also get two equal parts. So one is the mirror image of the other one. So that kind of action is called as symmetry. One side is mirror image of other side. When you cut about that axis, then we can see symmetry about a particular axis. But it is found that in I section, the section is symmetry about both YY as well as ZZ axis. So what is the benefit of having symmetry about both the axes? The advantage of having symmetry about both the axes is that the center of gravity and shear center coincides. So very important point which you have to understand is that in I section, I can say that in I section, both center of gravity and shear center coincides. In I section, both center of gravity and shear center coincides. Why? Since it is symmetrical, about both the axes. Because it is symmetrical about both the axes, therefore center of gravity and shear center coincides. So what is the shear center basically? So what is the shear center? Very simple thing. This is a very important point which you have to understand. What is the shear center? So shear center is a point through which when a resultant load is applied, there will not be any torsion. So it is the point shear center. It is the point through which if the resultant load passes, it is the point through which if the resultant load passes, there will not be any torsion. There will not be any torsion developed. There will not be any torsion developed in the section. So please understand, shear center is a point, you identify a point through which the total resultant load which is acting on the section passes, then there will not be any torsion. Torsion effect will not happen. Okay. So this is possible if the section is symmetry about both the axes. Any section which is symmetry about both the axes, then center of gravity and shear center coincides. Please underline this point. It's a very important point which tells us what is the efficacy or efficiency of a particular section. So because I section is symmetry about both the axes, therefore center of gravity and shear center coincides. Hence torsion effect is eliminated. So torsion effect is eliminated in case of I section because of the only reason is that it is symmetry about both the axes. So here the center of gravity is the same location and the shear center also same location. So the torsion effect is equal to here 0. So torsion is equal to 0 in this particular case because of symmetry. Because of symmetry, torsion is 0. Suppose if any section is unsymmetry about one axis, then torsion comes into picture. Okay. So that kind of sections additionally we have to design for torsion also. So I section we cannot design for torsion here because of unsymmetry. There is no kind of torsion comes here because it is symmetrical section. So I can say here is that in case of I section, so otherwise I can say that I section is designed for, I can say that, so I section is designed for bending moment, shear force alone or only because of symmetry. Okay, what is the only reason? Because of symmetry. So please try to understand this. Whereas, if you look at another section where symmetry is not there in both the axes, then you have to design for torsion also. Fine. So, very simple thing. Whenever I take, see, listen, you have to imagine that this is the only section I am drawing here. But imagine there is I section present over a length like a simply supported beam. You are keeping this I section as a simply supported beam. See, look at here. I am drawing a section. I am drawing simply supported beam here. One end is roller, other end is hinged. This is the I section, this is the beam, and this beam is made of I section. Let's say this beam is, which section it is? I section, whatever I drawn here, this I section is provided as a beam, but I am drawing a line diagram here. Now listen, whenever there is a beam, we design the beam for carrying certain load. So there is some uniformly distributed load. Then we have bending moment. We have bending moment in this beam, WL square by 8. We have shear force in this beam, WL by 2, W is the intensity of load, L is the span. We can have bending moment WL square by 8. We have shear force maximum value is WL by 2 at the supports. Fine. So that means this beam we have to design only for bending moment and shear force. Torsion effect is 0 because it's a symmetrical section. Okay, fine. Okay. Now understand, dear students, how many I sections are there? Okay. What are the different types of I section available? That means in I section itself we have some sub classification. We have 5 types of I sections. Okay. Before going into that, let me tell you one important point. This I section is also called as the beam section. Please understand, dear students, I section is also called as the beam section. Why this I section is called as beam section? There is a reason behind it. Why it is so? The reason is very simple. Look at here. Whenever you load any beam, what happens? There will be bending is going to takes place. Look at here. Let me explain in this way so that you can understand easily. Suppose if I have a beam, let's say this is the beam I am having. I am taking a rectangular section for understanding purpose. I can make it even I section also. But okay, let's say it's a simply supported. This is the I section, and okay, this is the shape of the, let's say rectangle. Let's say you take a rectangular beam. This is the shape of the beam before loading. Whatever I drawn is a line diagram, but beam is having some dimensions, width, depth and all. So I have drawn only depth here, width I am not shown here, but purposefully I will show it. Now this white line, whatever you see here, is the before application of load. Now what I am doing is, I am applying load on this beam. Once you apply certain load on this beam, it starts bending. So once you apply the load, this particular beam try to bend in this fashion. This particular beam is going to bend in this fashion. This is the deformation profile of the beam after bending. So this is after bending. What about this? This is before bending. So whatever the white line you see here, 1 minute. So whatever the white line you see here, that is the before bending. Okay. So this particular thing white is before bending. The shape of the beam is like this before bending, and the shape of the beam is yellow line after bending. Okay. So if you understand, dear students, if I draw an axis, there is one axis which is present throughout the length of the beam and which divide the compression zone and tension zone. See here, once the bending happens, there is a compression here in the top fibers. You can see here, see. This is the white line rectangular beam before application of load. I written here carefully, before bending or before application of load. Because when you apply load, bending also occurs. Before application of load, nothing but before bending also. So this is the rectangular box is the before bending. Once you apply the load, is nothing but yellow color one, it bend in the form of yellow color. So what happened is this white line, whatever is there here, has turned to like this. This position is shifted to this position. This line has turned like this. That means these fibers are being compressed. So compressed, this is what compressed. So above the longitudinal axis, the compression happened, but the bottom fibers are stretched. This is what happened. Stretching is happened below the longitudinal axis. That means that there is a tension below the longitudinal axis. So this particular axis is called as the longitudinal axis. Please understand, dear students, most of the students commit mistakes. You don't understand what is the longitudinal axis. Please understand carefully. So this particular axis, whatever you see here, is called as a longitudinal axis. This is called as the longitudinal axis. Okay, please understand this. So longitudinal axis, how do you define it? Longitudinal axis is an axis which is running throughout the length of the beam. Which is running throughout the length of the beam, parallel to the length of the beam. Longitudinal axis exists and which divide the compression zone as well as the tension zone. Okay, please understand that carefully. And above the longitudinal axis there is a compression. Below the longitudinal axis there is a tension happens. Now dear friends, you understand that this particular variation is linear. So there is a very important understanding, very important assumption given by our Euler-Bernoulli, people also call Euler-Bernoulli. So what Euler-Bernoulli told is that plane sections before bending, see this white line is before bending, remains plane. See, I am showing with example, see here, this white line is this marker. This is the plane section before bending. Now once I apply the load, it turns like this, but remains straight only, it is not curved. Na? This yellow line is not curved, it becomes straight only. So plane section before bending remains plane after bending. What is that assumption meaning? Which means that the deformation is linear. See here, this is a triangular variation, you can see that this is a triangular variation, that means linear variation. If you go away from this axis, the strains are more, deformations are more. And how it is varying deformations? Linearly. See, that is what I am trying to say. If the deformation is linear, then we can say strain is also linear. Here, very important thing you have to understand is that, so I am explaining what is the meaning of plane section before bending remains plane after bending. I am explaining the same thing here. So plane section before bending, plane sections before bending remains plane, plane sections before bending remains plane after bending, after bending. What does that mean? Which means that the deformation profile is linear, which means deformation profile is linear. Which means deformation profile is linear. The deformation profile is linear, we can say that therefore strain also varies linearly. So therefore strain also varies linearly. Please understand this. If the, what is the meaning of plane section before bending remains plane after bending? Which means that deformation profile, you see here, na, this is the linear. The deformation profile is linear, we can say that strain also linear. How can I say? Because we know that strain, epsilon strain is equal to deformed length by original length. Original length is always same. Whatever the way deformation varies, the same way strain also varies, because you know this, deformation is varying linearly. Just now we have seen that deformation is varying linearly from triangle. This shape is triangular variation is called a linear variation. So deformation is varying linearly. So therefore we can say that strain also varies linearly. That's all. Very simple as that. Okay. So the main meaning of plane section before bending remains plane after bending means strain variation is linear. Okay. So the same thing if I plot in a section, cross section, how it will be? Let us look at that. So when I take a cross section here, any section here, what happens? So this is what the section is basically. This is the cross section of the beam. Okay. So perpendicular to longitudinal, this is the longitudinal axis. Perpendicular to longitudinal axis, there is one axis called as neutral axis. So always remember, neutral axis exists only in the cross section. Very, very important point. Neutral axis we can never find lengthwise. Neutral axis exists only in the cross section. Please make a note of that. So because this deformation profile is linear, we can say that strain profile also varies linearly. Okay, so that is what very important thing which you have to understand. Okay, so let me erase this. Let me rewrite the same sentence here. It was erased. Just a minute. Okay. So just there is no space available. Okay. So I can draw the same thing here in this manner. I am writing very close to this. The strain varies linearly and strain at neutral axis is 0. Strain exactly at neutral axis is 0. Please remember that strain is maximum at topmost fiber and strain is maximum even at the bottommost fiber. Please understand that. So strain varies linearly. That is the Euler-Bernoulli assumption. Strain is 0 at neutral axis. Epsilon means strain. 0 at neutral axis. Strain is maximum at topmost fiber and bottommost fiber. That means maximum compression occurs top and maximum tension occurs at the bottommost fiber. Okay, which is what you have to understand. So now I am trying to say why I am conveyed all these things to you. There is a reason behind it. See here, beam undergoes vertically downward load. Please understand, this is the beam. White line, whatever rectangular box, white box you see here, that is the beam, is subjected to vertical loading, vertically downward loading. What is that? Vertically downward loading, which is called as transverse load. So beams are always subjected to transverse load. Please remember this. Beams are transversely loaded structural members. That transverse load causes bending moment and shear force. If somebody asks you what is a beam means, beam is a structural member which is subjected to transverse loading which causes bending moment as well as shear force. That is how you have to define. Now understand, dear friends, when there is a transverse load, bending is occurring about which axis? See here, this plane section remains plane after bending. About which axis this is turned compression and tension? See here. That is what you have to understand. This visualization is very, very important. See, actually beam is not this strip. Beam is having certain width and depth. So I am drawing in 3-dimensional figure. Let's say beam is having some width. Now I am drawing 3-dimensional. This is what. So this beam is having certain width. Do you agree with me? Yes. This entire beam which is in white color before loading has turned to yellow color this much. This is how it is turned. About which axis it is turned? That is a question mark. About which axis this is turned? That is the biggest question mark. What is the answer for that? This fellow has turned to this. Okay, fine. This is how it happened. Right? This is being stretched in this manner. About which axis this has turned to compression and tension? This is the axis. About this axis, which is called as neutral axis or horizontal axis, about which bending is happened. Please make a note of that. When you apply a transverse load, it undergone compression and tension. About which axis it undergone compression and tension? By taking the neutral axis as the reference. So, my dear friends, very important thing, when there is a transverse load, bending occurs. That bending causes compression and tension, above neutral axis compression, below neutral axis tension, and bending is happening about one horizontal axis which is called as neutral axis. Please understand, bending occurs about the neutral axis. Please understand that. That is what same thing I am going to write over here. Make a note, very important note is that bending occurs about neutral axis. Please understand this. Bending occurs about neutral axis. So whenever I talk about bending, my axis of concern is neutral axis, which is the horizontal axis. Okay, so in bending equation or bending formula, we have bending formula m by I is equal to sigma by y or f by y. In this, essentially I am going to use m is equal to f by y into I. This I, whatever I am going to use, that I must be about the neutral axis. The neutral axis called itself is the horizontal axis, which I call it as ZZ. So I must use always IZZ, because I should take about moment of inertia about neutral axis, because whenever I say bending, whatever the axis about which bending is happening, about that axis only we should take the neutral axis. That is what I am trying to say over here. So in bending formula, we always take moment of inertia about neutral axis. Clear to everyone? Hope it is clear to everyone. But when I talk about bending, that is a different thing. When I talk about, okay, bending is two types. One is the moment actually. Moment is of two types, bending moment and torsional moment or twisting moment. So torsion, when I talk about torsion, torsion is different from bending. Okay. So when I say torsion, suppose you take this kind of action and you twist the member, two equal and opposite couples you apply, then it twists. Okay. The torsion is occurring about the lengthwise axis, which is called as the longitudinal axis. So torsion always occurs about the longitudinal axis. Please understand that. So whenever torsion is there, in torsion equation, we use the moment of inertia about the polar axis. So please try to understand that. So torsion is a moment. When I talk about torsion, I can say that torsion, it is the moment about longitudinal axis. It is the moment about longitudinal axis. Okay, please try to understand this. It is a moment about longitudinal axis which is called as the torsion. So whenever there is a torsion comes, we always use the moment of inertia about longitudinal axis. This longitudinal axis is called as the polar axis. It is also called as the polar axis. That means which is perpendicular to both cross-sectional axis, called as the polar axis. That's why, look at here, whenever I say torsion, see here, this is what, if the member is like this, maybe circular also or non-circular also, doesn't matter. Let's say circular thing for understanding purpose. So when you twist it, basically when you twist it, when you apply some moment, two equal and opposite forces, this is what torsion is. So torsion comes into picture. So torsion occurs about the longitudinal axis. So please understand that. So in the case of torsion equation, I can use T by J is equal to tau by R is equal to G theta by L. Okay, anyhow G theta by L we are not going to use. So when I say torsional carrying capacity, if I want to estimate, I have to use tau by R into J, where J is nothing but polar moment of inertia. Which moment of inertia? Where J is called as the, is also called as IP, which is nothing but polar moment of inertia. Polar moment of inertia, which is okay. So a section which is having more polar moment of inertia will take more torsion capacity. A section which is having more moment of inertia about neutral axis will take more bending. Very simple logic. Any section which is having more moment of inertia about neutral axis, and neutral axis is always a horizontal axis, then it carries more moment. If any axis having more moment of inertia about polar axis perpendicular to cross section, then it takes more torsion. So how do you get polar moment of inertia J? So J polar moment of inertia, which is also some people call it as IP also, which is equal to Ixx plus Iyy. So summation of moment of inertia about, in steel structures, I already told that, say I written ZZ, horizontal axis. In normal sections we write XX, YY, but steel structures there is a limitation that in steel structures horizontal axis every time we take ZZ, okay. So we can write Ixx or Izz, we can say Izz plus Iyy. That will give you essentially the polar moment of inertia, okay. I hope you understand this. Izz plus Iyy, which will give you polar moment of inertia. So more polar moment of inertia, more torsion it can resist. I hope you understand this particular thing. Now, Let us go ahead with, okay. So what I told earlier, if you look back to here, this particular slide you look at, I section, as I told that, it is, see, very important point is that why I have shown ZZ as a horizontal axis and vertical axis YY. See, you might have drawn every horizontal axis so far as XX and vertical axis as the YY. But listen, our Indian standard is saying that in order to avoid the confusion, if it is a steel structure, structural steel, better you represent horizontal axis with the ZZ so that everybody understand that it is a steel section. So to identify steel section which is identical or different from other sections, take horizontal axis as the ZZ and vertical axis as YY, which implies that it is a what section? Steel section, structural steel section. That is what you have to understand. Fine. Now understand, dear friends, as I told you just now, moment of bending moment occurs about the neutral axis, torsion occurs about the polar axis. That is what I told you. Now come to the point here, as I told just now, in I section, ZZ axis is called as major axis, YY axis called as the minor axis, which means that as I section is having more moment of inertia about ZZ axis, it can take more moment about ZZ axis. But the same thing is happening in bending also. In bending, just now I told that bending occurs about the ZZ axis. Am I correct? If you want, just look back. Look at here, this is what I told. Bending always, I written the moment, I can say bending moment so that it will be very clear to you. So the bending moment, let me tell you, I written already in top, here not here, top. So bending occurs about neutral axis. This is a very, very important point. What is the neutral axis in I section? Go back and see. This ZZ axis is the neutral axis. So I section, if you observe carefully, I section is the section which is having more moment of inertia about ZZ axis, which is also called as the neutral axis. Therefore, it can take more moment. So, my dear friends, very important conclusion is I section is the only section which is having largest moment of inertia about its horizontal axis, which is in fact neutral axis. About that bending is occurring. So, a section which has highest moment of inertia about a neutral axis is the most efficient section to resist the bending. Is it clear to everyone? Which is proved already. So, you have to understand just already proved by the researchers, proved already, right? But your understanding in the examination they are asking this kind of things. So, I am trying to say here is that in case of bending, the most efficient section we can go for is I section. That is what I am trying to say. So, I can say here, when compared to, very important note is that, when compared to rest of the sections, the remaining sections, for a given area, for a condition is what? For a given area, I section provides, for a given area, I section provides larger moment of, I section provides larger moment of inertia about its horizontal axis, nothing but neutral axis. Therefore, it is the most efficient section. Therefore, it is the most efficient section. Therefore, it is the most efficient section to resist bending. Okay, please try to understand this. The most efficient section to resist bending is this section. What is that? I section. So, in the any competitive examination you write, if they ask a question, which of the following section is the most efficient section to resist bending? Then the correct answer is I section itself is the correct answer. So that's why our Indian standard is saying that I section itself is called as beam section. Therefore, I section itself is called as, or I section is also called as, I section is also called as beam section. I section is also called as the beam section. Please remember this. Okay. Now the beam sections are how many types? How many beam sections are available? What are the types of I sections? Let us look at one by one. So types of I sections, what are those? What are the practical applications? So we'll see all of them one by one. So let us look at that. So types of I sections. So types of I sections or beam sections. What are the types of I sections or beam sections? Let us look at that. The first thing is that we have ISJB. What is the meaning of ISJB? Indian Standard Junior Beam. Indian Standard Junior Beam. The second one is Indian Standard Light Beam, or people also called as light beam or lightweight beam. Both are same, there is no difference. And we have something called Indian Standard Medium Beam or Medium Weight Beam. Indian Standard Medium Beam. And we have even Indian Standard Heavy Beam, HB. It is also called as Heavy Beam. Indian Standard Heavy Beam is the HB. So these are the, okay, and one more thing, 5 sections. Indian Standard Wide Flange Beam, WB means Wide Flange Beam. So these are the 5 types of beam sections that is available. So one of the question asked in the GATE exam was, beam sections are classified into, what is the correct answer? Beam sections are classified into 5 types. Please understand that. What are those? Junior beam, light beam, medium beam, heavy beam, wide flange beam. Now coming to the practical applications. So where we use junior beam? So Indian Standard Junior Beam, which we generally used for vehicle manufacturing purpose. We are not going to use as a structural member most of the cases. In few cases may be possible, but most of the circumstances, this junior beam we use for manufacturing of vehicle parts. For example, look at trucks or look at any kind of vehicle. Look at bus otherwise. When you look at a bus, when you're standing on the bus, if all seats are filled, you will be standing over the plate. That is what we call plate, platform, whatever you see there. So do you think that that plate itself is taking the entire load? No. So below that plate where you are standing, there are beam girders, I section girders are there below that. And those I girders are resting on the actually axle. Okay, that is how the load distribution is taking place. So that is what you have to understand. So my dear friends, for those I sections, we go for the junior beams. So junior beams are used for vehicle manufacturing purpose. And light beam and medium beam, these are very, very important. Most of the floor girders or beams, for beams, we go for this one. And junior beams, we go for vehicle manufacturing purpose. So vehicle parts are made of this junior beam. And heavy beam generally we use for columns. So you may be surprised basically. Yes. So beams, as I told just now, the most efficient section for beam is I section. Very, very important point, which is asked several times, which is asked in different competitive exams. Please understand, dear friends, because I section is the efficient section for beams, beam has to rest over the columns. Okay. So my dear friends, beam is a I section, and column also, if you provide I section, it is very easy to connect one I section with the another I section because we have good amount of flange width, etc. you have flanges, 2 flanges and 1 web, we can have a good connection between these two. So, based on the practical aspects, I section is the best section even for columns also, just by keeping in view of practical limitations. But most efficient section for column is different. I will explain that. Afterwards, I will explain in a sequential manner. But for the time being, understand, I section is not best section for column. It is not correct. But connecting best beam section with the best column section is not possible. That is why we are taking sometimes, even though some ideal things are there, because of connectivity issues, practical problems, we cannot go for ideal members. We can go for relatively good members because of the limitations of connections. Connecting circular hollow section with I section is very difficult because most efficient section for compression is circular hollow section. But connecting I section, which is beam section, with circular hollow section is very difficult. That is why keeping in that practical limitation, we can go for even columns also, we can go for the I section. So, among these, heavy beam, ISHB, heavy beam has more radius of gyration. That is why it can be used as a column. I will explain about what is that, exactly I will explain that. Just for time being you understand, for heavy beam is used for columns. And wide flange beam is used for gantry girders. What is this? Gantry girders. So, I will explain about what are the gantry girders, all these things. Okay, gantry girder, there is separate chapter, I will explain there what is a gantry girder, what are the loads acting on gantry girder, all those things I will explain. So, for the time being, if you want, I will explain what is a gantry girder. So, in industrial buildings, look at any big industry, there is a heavy load you have to shift from one place to another place. Whenever you want to shift heavy load from one place to another place, we need to have strong girders. Okay, so for example, let us go forward. So, I will explain this gantry girder in this fashion. So, look at here, my dear friends, I have a crane. This is the crane I am having. Let us say this is the crane I am having. This is the crane I am having. And we have, these are the members which are there in the crane, and these are the connecting members, let us say truss, because let us say this is the truss crane, and we have wheels that are coming out from this crane, and these wheels are going to rest over the, let us say I have a column, so I have to basically provide this crane on the top of the column. See, look at here carefully. How can I provide this? Very simple thing. There is some wheels which are coming from this, and these wheels are directly rest over the a section which is called as the gantry girder. This is what it is. Just I am summarizing here in a simple manner. There is a wheel load which is coming from the crane. That wheel load is going to move over the rail. This is the wheel load actually. This is the wheel which is coming from the crane. This particular wheel is going to move over the rail which is placed over a particular girder. This is called as the gantry girder. Just briefly I am explaining this, but I have separate chapter we have. There I will explain about the gantry girder completely. See here, this is the column section, this is also the column section, and we have, this is the gusset connecting plate member, this is what the connecting element is, we have the connections like this. Now understand, dear friends, please understand that crane, this is crane. So, listen, symmetrically, this is the column actually. So, we have column of certain height above the ground level. This is the column. I will explain, just do not worry. This is the gusset plate or connecting plate or bracket plate, whatever it is, not gusset plate, it can be bracket plate, I can say, most appropriate word, bracket plate. Okay, please understand, dear friends, this is the bracket plate. On the top of this bracket plate, we have the what we call girder. See, there is a crane wheel load. This is the crane actually. This is the crane. So from the crane, the load is passing through wheels over the rail. This is the rail actually. This is the rail. This rail is provided over the I section. Railway track, nothing but track. The wheels of the crane is this one. They are rotating over this. This gantry girder is, this is called as gantry girder. Whatever you see, this is the gantry girder. So my dear friends, please understand, I'll explain once again, don't worry. It's a very, very simple concept. Look at here. So there is a one vehicle, this is called as a crab. From the crab, there is a hook arrangement. To this hook arrangement, we place this certain load. This is the load we are having. So my dear friends, please understand, this is called as the crab. This is the crab, a vehicle. From this, there is a hook arrangement and the load is supplied to that. Then this crab is moving here and there in the industry. See, listen, imagine industry. You want to shift heavy loads in the industry from one place to the another place. You have to shift heavy load in an industry from one place to the another place. For that, we require the crane. Crane is required because crane is the one which is having enough strength to bear that kind of load. That's why it's called as crane, basically. Now listen, this particular load, I want to shift both laterally in the industry as well as lengthwise throughout the industry. Imagine industry which is a very long industry. I have to shift loads in the industry from one place to another place lengthwise as well as the widthwise. So that's why I require a crab. I attach a load, and if I want to shift the load laterally, I switch on the crab will move. There is a track. Listen, wherever wheels are there, below the wheels there is a track. So that when I switch on the motor, it will move. Okay, fine. Right. Next, this entire load, whatever we are lifting, self weight of all these things, ultimately has to transfer through wheel of a crane. From the wheel of a crane, it transferred to the gantry girder. Because listen, very important thing is, in industrial structures, to support heavy load, we require a very strong beam. That strong beam which is used to support heavy loads are called as the gantry girders. I hope it is clear to everyone. Gantry girder is a beam. It is a beam which is provided in industries. This is the gantry girder. Please understand this. This itself is the this I section itself is the gantry girder. So gantry girder is a beam which is provided in industrial structures to support crane loads, heavy loads, and which will transfer the load to the column. Very important thing is, throughout civil engineering we talk about load must transfer from beams to the columns. Okay, please understand. From the horizontal member, load will transfer to the beam, then from beam it is transferred to the columns. The same thing is happening here. Imagine same thing is there here also. It is not in air. Just for otherwise I write symbol called continuity. So this is continuous. The same thing is there on the other side also. Okay, I hope you understand this. So what are the loads acting on gantry girder? Very important thing, my dear friends. When I apply the crab, see, look at here. When I switch on crab moves. When the crab moves, it is going to cause lateral thrust. It is going to cause lateral thrust onto the gantry girder. So crab movement is going to cause lateral load on gantry girder. It's very important. This kind of questions also they are asking in the exam. Okay. So this is the y-y axis. This is the y-y axis. Crab movement causes this kind of lateral load. Please remember this. Crab movement causes lateral load. Crab movement causes the lateral load. And self weight of the crab, crane, everything is going to cause the transverse load. This particular load, vertically downward load, is called as the transverse load. Okay. Transverse load is causing bending about z axis. I already told, any load which is acting downward is going to cause bending a moment about z axis. Any load which is parallel to the z axis is going to cause bending moment about y-y axis. If you want, I'll explain again. Just understand this. Load, okay, transverse load causes bending about z axis. I can say here, transverse load causes transverse load causes bending about major, that means ZZ, major axis or ZZ axis. Transverse load causes bending about major axis or ZZ axis. Next, that's what I am trying to say. Next one is lateral load. Lateral load causes bending about minor means YY axis. Lateral load causes bending about minor axis or YY axis. So please understand, dear friends, I am writing here again, if I have Y axis, I section like this, so this is what the YY axis is and this is what the ZZ axis is. So understand, dear friends, any load which is parallel to transverse direction, this load is the transverse load, this load is the transverse load which causes bending about ZZ axis. Transverse load causes bending about ZZ axis. Now one more thing, see, understand, this is the lateral load. This is the lateral load. This lateral load causes bending about YY axis. Lateral load causes bending about YY axis. Please remember that. That means, see, whatever the axis it is bending, about that axis if you provide more moment of inertia, then it is strong about that axis. It can effectively resist that load. What is the meaning of that? Let me repeat the sentence. Transverse load, we know that, causes bending about ZZ axis. So, to resist transverse load effectively, the section should have more moment of inertia about ZZ axis. Okay? We have lateral load. Lateral load causes bending about YY axis. Lateral load causes bending about YY axis. Therefore, to resist lateral load effectively, the section should have more moment of inertia about YY axis. This is the very simple logic you have to understand. To resist transverse load effectively, the section should have more moment of inertia about ZZ axis. To resist lateral loads effectively, the section should have more moment of inertia about YY axis. Is it clear to everyone? That's what. If you have this much clarity, you can choose the section comfortably. Look at here, dear students. In case of gantry girder, crab movement causes the lateral load. So, which is the dangerous load? Very important thing is, suppose you are standing like this, and if your friend is applying load like this by keeping his your friends are keeping your bags like this, you can bear the load easily. It's a transverse load. But the moment not applying the load like this, but your friends are going to push you laterally, you will become more unstable. The most dangerous load is the lateral load. So, small amount of lateral load is going to cause instability of the structure. So, the critical load in case of gantry girder is the lateral load. The critical load in case of gantry girder is lateral load. Okay. So we should be very careful when you design the gantry girder, as lateral load is very critical. We need to have more moment of inertia about YY axis. So, we have to search for a section such a way that should have more moment of inertia about YY axis. So, my dear friends, please understand this. Among all the available sections of I section, like junior beam, light beam, medium beam, heavy beam, wide flange beam, among all these sections, it was observed that wide flange beam has more moment of inertia about YY axis. Please understand this. So, that's why a wide flange beam has large moment of inertia about YY axis. Make a note here that why we are using wide flange beam as a gantry girder. In gantry girder, very dangerous load is a lateral load. Just now I explained. And lateral load causes bending about which axis? YY axis. So, among all the I sections, I can say here that among all the I sections, among all the I sections, ISWB, Indian Standard Wide Range, ISWB provides larger moment of inertia. ISW provides larger moment of inertia about y axis. Therefore, what does it mean? Therefore, it has more lateral resisting capacity. Therefore, it has more lateral resisting capacity. Therefore, it has more lateral resisting capacity. So, that's why we provide the ISWB itself as the gantry girder. Best section for gantry girder is ISWB. Now, I told one more thing, I will explain that. Why we are providing heavy beam for columns? There is a reason. I will explain that now. Okay, I hope you understand. One of the question asked in the GATE exam was, what are the loads acting on gantry girder? So, we have transverse load, that is one of the load acting on gantry girder, and we have lateral load, that is another load acting on gantry girder, transverse load, and we have even something called impact load. So, this crab and crane, suddenly it moves. So, impact load also comes, and this crane, see here, this crane wheel is moving like lengthwise. Lengthwise, whatever the load acts is called as a longitudinal load. So, gantry girder also subject to longitudinal load. So, gantry girder is subject to transverse loads, lateral loads as well as longitudinal loads. These are the three types of loads predominantly acting on gantry girder. But among those, the most dangerous load is the lateral load. Wind load, do you consider wind load for gantry girder? No, not at all, because when compared to these loads which are heavy loads, that wind load is very small, and inside the structures we are having this kind of things. So, one more thing, to improve the moment of inertia about y-y axis, most of the time above the gantry girder I section, we provide the channel reinforcement. This is also very commonly asked question. In order to improve the moment of inertia about y-y axis and to provide more lateral stability, above the I section we provide the channel reinforcement, that is channel section. This is a very popularly asked question. So, please try to understand that. On the top of the I section, generally we provide the channel section as a reinforcement, which will enhance the moment of inertia about y-y axis, and it will resist the crab load moment. Okay, I hope you understand this. Okay, now coming to another thing, what I can say is, why heavy beams are provided for columns? There is a reason. So, Euler's critical load carrying capacity of compression members as per Euler's formula or Euler's formula. So, as per Euler's compression load carrying capacity, if you want to find as per Euler's theory, so compressive load carrying capacity or critical load carrying capacity, compressive load carrying capacity. The compressive load carrying capacity PCR is given by formula. What is the formula? Pi square EI by LE square. Pi square EI by LE square. This is the critical load carrying capacity of compression member. Okay, fine. As we know that this PCR is equal to pi square E. What is I? I is the second moment of an area, which is equal to AR square by LE square. So, we can write this as pi square EA by LE by R whole square. Okay. So, I can write the critical load carrying capacity is equal to pi square EA by lambda square, where lambda, I written lambda as LE by R minimum. Okay. So, please understand, dear friends, the critical load carrying capacity of a compression member as per the Euler's theory or Euler's theory, The critical load carrying capacity of a compression member is given by formula pi square EA by lambda square, otherwise pi square EA by LE by R whole square. So, my dear friends, the length of the column is fixed. Based on end conditions, effective length of the column is fixed. So, we cannot change anything about length, but I want to improve the load carrying capacity. How I can improve the load carrying capacity? That is what my question is. How can I improve my load carrying capacity? When I want to improve my load carrying capacity, I have to reduce only slenderness ratio. That's the only option available. The only option available is I want to reduce the slenderness ratio. If the slenderness ratio is less, then load carrying capacity is more. How can I reduce slenderness ratio? Very simple. I cannot change length. If I want to reduce my slenderness ratio, I have to increase my R minimum. So listen, this is a very, very important point when I talk about compression members. Whenever I talk about compression member, this point you have to understand. What is that? So radius of gyration, least radius of gyration or minimum radius of gyration should be high. If a section which is having highest minimum radius of gyration provides less slenderness ratio, if it provides less slenderness ratio, which leads to higher load carrying capacity. So for the compression members, how do you say a particular section is a most efficient section? The criteria is radius of gyration. The section which is able to produce higher minimum radius of gyration is going to give larger load carrying capacity. So that's the very important point which you have to understand. So I can make a note, I can write a note over here so that you can understand it, revise it whenever it is required. So whenever you want to have higher load carrying capacity in the compression, you should have highest radius of gyration. Okay, the section which has highest radius of gyration, the section which has highest minimum radius of gyration, the section which has highest radius of gyration, the section which has highest radius of gyration provides, section which has highest radius of gyration provides more compressive capacity, more compressive load capacity, more compressive load carrying capacity, more compressive load carrying capacity. So please understand, dear friends, when a particular section has to carry heavy compression load, it should have less slenderness ratio. That is possible when you have highest radius of gyration. So whenever you talk about compression members, the very important parameters which governs the load carrying capacity is radius of gyration. Please remember radius of gyration. Radius of gyration, if it is high, then it is the best compressive load carrying capacity member, I can say. So the best compressive load carrying capacity member is the member which has the highest radius of gyration. Is it clear to everyone? I hope. So my dear friends, now come to the previous things what I told here. I told that heavy beam is provided for the column. See, why I told that? There is a reason. Among all these 5 I sections, how many types are there? I sections are? Please remember, this question also asked in the GATE exam. So I sections are classified into how many types? 5 types. Please remember that. The beam sections are classified into, what is the correct answer? 5 types. Please understand that. Among all these 5 I sections, ISHB is the only section, which has the highest radius of gyration. Hence, it carries heavy load carrying capacity. Okay, highest compression capacity it carries. That's why ISHB sections are provided as the columns. I hope it is clear to everyone. Okay. Now, let us move forward. Right. That is all about I sections. Now, how to designate I sections? That is another important thing. So, I sections, how to designate that? So, I section is designated as, example I am saying here, I section is designated as like this. Example I am saying, let's say ISMB 600 @ 735.8 Newton per meter. So what does it mean? This is how the I section is designated. So number after ISMB is representing the overall depth of I section, representing the overall depth of the I section. At the rate Newton per meter, that is giving you the self weight per meter length. This is the self weight per meter length. Self weight per meter length is this one. So this is how we designate the I section. Okay, please try to understand it. Okay, so the number after any IS beam represents the overall depth of the I section. At the rate something Newton per meter is nothing but self weight per meter length. So that is how we designate the I section basically. Now, once you know about the I section, where we can use I section? I told several applications. Beams, best section is I section. Columns also we can go for, okay, anywhere. So it has a lot of moment of inertia about the major axis, fine, okay. Now come to the second type of section, which is called as the channel section. So I section is very important, that's why I talked this much about I section. Now let us move forward to the second type of section, which is called as channel section. So channel section, how the channel section appears like. Okay, so when I look at channel section, essentially how it looks like, see, the channel section is something like this. It also has two flanges and one web. These are the flange. This is the flange, this is the flange, and this is the web. The channel section also has two flanges and one web. And essentially, look at here carefully. So we have axis. This is the horizontal axis, and this is the vertical axis. This is the YY axis, and this is the ZZ axis. Okay, this is the major axis, that is the minor axis. Fine. Now, what is the problem with the channel section? That is the question mark here. What is the problem with channel section? The problem with channel section is that it is unsymmetry about one axis. So what is that? Can you please identify which axis about which the channel section is unsymmetrical? Very simple. So if you cut about YY axis, I am cutting about YY axis. So when I cut about YY axis, you get this piece separate and these two small pieces separate. So it's not symmetry about YY axis. But when I cut about ZZ axis, this is the ZZ axis. When I cut about ZZ axis, so upper part and lower part are, one is the mirror image of the other. So that is what you have to understand. So channel section is symmetry about ZZ axis, but unsymmetry about YY axis. So I would like to tell here is that channel section is unsymmetry about YY. So channel section is unsymmetrical. Channel section is unsymmetrical about YY axis. So that's the biggest problem, but symmetrical about ZZ axis. So my dear friends, the very challenging task when you design channel section is unsymmetry is the problem. So because of the unsymmetry, what happens? So because of unsymmetry, there is no chance of coincidence of center of gravity with shears. This is the center of gravity. Okay, but because it is unsymmetrical about YY axis, then shear center will not coincide where centroid is there. So shear center lies somewhere outside the section. So very important, my dear friends, very important point is that the shear center always lies along the axis of symmetry. What the very important thing is, shear center always lies along the axis of symmetry. So what is the axis of symmetry here? ZZ axis is the axis of symmetry. So at this point we can have shear center. So very important point, the biggest problem with channel section is the shear center lies outside the section. That is the biggest problem because of unsymmetry. Okay, so this was the question asked in the GATE exam earlier. So for the channel section, the shear center lies outside the section. Fine. They ask the question in this manner. They given same question, same figure, and they given A, B, C. A here, B here, C here, D here. Identify which point represent the shear center. So this point itself representing the shear center. So in the channel section, shear center lies outside the section, and that is there along the Z axis. Please understand this. Fine. There are some procedures to find shear center, that is not at all required here. It will be taught in engineering mechanics. Fine. Now come to the point. If the center of gravity and shear center does not coincide, what is the problem? So there will be a torsion we are going to get. So because of this, whenever you apply load, this eccentricity builds up and this section undergoes the torsion. So please understand, dear friends, because of unsymmetry, you are getting a torsion. That is the challenging task. So channel sections are always designed for torsion. Please understand this. So I can say, in addition to bending and shear, we have to design for torsion. So channel sections are always designed for bending moment, shear force and torsion. Channel sections are always designed for bending moment, shear force and torsional effects. Torsion must be there. So that is another typical task every engineer has to focus on, okay. But in I section, we need not to design for torsion. That is what I told. Now, there is another question asked in the GATE exam. The another question which was asked in the GATE exam was as follows. So the question was, there is a channel reinforcement provided. This is what it is. This is the channel reinforcement. Now the question comes, why this angle section is provided to the channel section? That is the question mark. Very simple. Question is very simple, which was asked in the exam. Now you have to answer this question. To the channel section, the angle section is attached. The reasons for this are: option A, to increase the area; option B, to increase the moment of inertia about y axis; option C, to increase the moment of inertia about z axis; option D, to make the load to pass through the shear center. What is the correct answer? See, when I provide the angles, you have to think logically here what the intention of the question paper setter. So when I weld this angle, yellow color angle section to the channel section, the load which is transferred here is going to shift to here. Then the load will pass through the shear center. When the load passes through shear center, we can eliminate the torsion effect. So angle section is attached to the channel section in order to make the resultant load to pass through the shear center. When the resultant load passes through the shear center, then there will not be any torsion developed in this section. So that is the very important point which you have to understand. So this angle section is attached to make the load to pass through the shear center. Is it clear to everyone? That is the significance of this question asked in the competitive exams. Okay, so that is what it is. So if you want, I will write that. So angle section is attached here. So angle section is attached. Angle section is attached to channel. Angle section is attached to channel section to make the load to pass through. To make the load to pass through the shear center. To make the load to pass through shear center. Hence, the torsion can be eliminated. That is the purpose of providing the angle section to the channel section. I hope it is clear to everyone. Now let us come to the next thing. In case, okay, when do you provide channel section? That is the question. So channel section, if you observe carefully, it is almost half of a section. See, when I draw one more flange this side, it becomes a I section. That means channel section is almost half of a I section, almost, not exactly. Mostly, most of the time, a channel section is a half of a I section. Okay. Now understand, that means this channel section is not having capacity equal to that of angle section, which is having a less capacity than I section. So, channel section has less load carrying capacity, less moment carrying capacity when compared to the I section. So, I section is provided as a beam or girder, as I told earlier. The most efficient section for beam or girder is the I section, I section, I section. You have to remember this, a very, very important point. For beams or girders, you always have to go for the I section only. Fine. But listen, every time you need not to choose the best section. There are some beams which are subject to light bending, little amount of bending, little loads, small amount of loads. In such cases, every time we need not to go for the best one. We can compromise with the channel section also. So, that is why channel section is provided as the secondary beam. So, please understand that channel section is provided as the secondary beam. Please make a note of that. So, channel section is provided as a secondary beam. Channel section is provided as a secondary beam. So, that means example like lintels. So, when I have a door opening, when I have openings of doors or windows, essentially I go for the lintel. So, lintel is the beam over the door openings. So, like this lintels, these are the brick or wall loading on these. This is the door or window, let us say, it is a door, or it can be even window as well. For doors or windows, we go for the, on the top of that we provide the lintel to support the masonry load. That's kind of beams are called a lintel. But if you want to go for steel section as a lintel, not RCC, let us say for example, we can go for channel section, need not to go for the I section, because I section is very stronger, more area, more material. How do you purchase steel? More material means more weight. We purchase steel in terms of weight. More weight means more investment. It will become uneconomical. So, the very important thing for civil engineers when you design something is you have to think cost effectiveness also. Very, very important. Economy plays a vital role when you do any design. If you give economical solution, safe solution, people will really appreciate your design and people will come to you actually. If not, so nobody turned up for you, to design something, to ask you for something design, etc. Okay. So, fine. So, lintels, suppose you look at in case of roof trusses, there is a beam called what we call purlins. So, in case of roof trusses, especially essentially this is one truss. We have one more truss somewhere here. We have one more truss. This is the one more truss we are having. This is the columns, whatever the lines are shown columns. So, this is the one truss, this is one truss, this is the another truss, this is the one truss, another truss, there is the spacing of truss. In between, see here, look at any industrial building or metro station, railway station, one truss to another truss, there is a gap. We have to provide sheeting. In any industrial structure, we need to have a roof sheet. Otherwise, what happens? We will not get protection from rain, sun, etc. So, we need to cover with roof sheet. Roof sheet is having a thickness less than 5 mm. So, whenever heavy wind comes, it buckles. That is the biggest problem we are having, buckling will happen. So, in order to arrest that, we need to have purlins. We have to provide the beams like this. These are the beams which are provided in between the roof trusses. We call them as the purlins. So, these are called as essentially purlins. So, purlins are the beams. So, purlins are the beams which are provided in roof trusses to support the roof sheeting. To support the roof sheeting, we provide the purlins. And understand, my dear friends, these purlins, do you go for I section? Not required. Just to support the roof sheet, very, very light sheet, do you go for I section? Not required. So, we go for purlins also with the channel sections. We used to use earlier, but now people are smart and we have a lot of improvements. We can go for Z type sections also available for purlins actually. Earlier we used to use channel section as the purlin. And listen, there is something called as built up column. What is that? We call it as built up column. Let us talk about what is a built up column. So for example, you want to apply a compressive load on a member. This is one member we are having. If you apply load on one member is having some capacity, limited capacity. When there is a heavy load comes, then single member cannot take the load, but it may exceed the capacity of the member. So in such cases, what we do is we provide two identical sections nearby. This is one section, this is another section. We place nearby and then we connect these two sections with lacings or battens. The inclined members are called as the lacings. These are the inclined members which are called as the lacings. And top we provide tie and bottom also we provide the tie. Okay, and we connect like this. Hope it is clear. This kind of columns are called as basically built up columns. These are called as the built up columns. These are the built up columns. So built up columns means when there is a heavy load comes, to sustain heavy loads, one section may not be sufficient. We connect two sections and make them as a single column. Such kind of columns are called as the built up columns. So this is what exactly we are doing. We apply the load here, and let's say total load is PU, and half of the load is transferred to this and another half load is transferred to this. So this is how the built up columns works. Is it clear to everyone? So heavy load came, half of the load is taken by one column, half of the load is taken by one column, because one section may not be able to sustain the heavy load, because we want to transfer heavy load. One section may not be able to sustain. In such cases, we go for the built up columns. I hope it is clear to everyone. For this kind of built up columns, you need not to go for I section. This section itself is sufficient. Channel section itself is sufficient, because let me tell you why it is. Because if you go for I section, yes, it is good, but the problem is economy is also criteria for us. This is the channel section, let's say. Instead of channel sections, if you go for I section, two I sections, one I section itself is having more capacity. For example, I want to transfer a load of 2000 kilonewtons, but one I section is having a capacity of, let's say, 1600 kilonewtons. One I section, let's say I section is having a capacity of 600 kilonewtons. Channel section is having a capacity of, let's say, 1100 kilonewtons. Which is the best one? Because see, if I provide one I section, it can take only 1600 kilonewtons, but our load to be carried is 2000 kilonewtons. If I provide two I sections load carrying capacity is how much? 2 into 1600, which means 3200. What is the load actually to be carried? 2000. That means I sections are safe, but they have more capacity than what we have to apply, what we have to carry. But here two channel sections should take it. What is the capacity of two channel sections? 1100 plus 1100, 2200. 2200 is more than sufficient to carry 2000 kilonewtons load. That means for economy, instead of going for two I sections, it is preferable to go for the two channel sections. Two channel sections itself are sufficient to carry the load. Okay, I hope you understand. For economy is placing a vital load when you go for any kind of construction. Fine. That's about channel section. So channel section is provided as a secondary beams. Wherever there is a light bending, we go for the channel section instead of the I section. It is clear to everyone. Okay. Now let us move on to the third. Okay, how to designate channel section? That is also the question mark. So channel section is designated as same as I section. There is no difference. So channel section is designated as, How it is in channel section? Very simple. ISJC, junior channel, let's say 300 at the rate 410.8 Newton per meter. This 300 whatever I have shown here is the depth, same as I section. First number after this section is overall depth, and another one is the self weight. This is the self weight, this is the overall depth of the channel section. Okay, overall depth of the channel section. Hope clear to everyone. How many channel sections are there? 5 channel sections are there. Junior channel, light channel, medium channel with parallel flanges, medium channel with sloping flanges, and gate channel. So these are the different 5 types of channel sections we are having. If you want, I will write here. So what are the types of channel sections we are having? Here also 5 we are having. What are those? Indian standard junior channel, Indian standard light channel, Indian standard medium channel, Indian standard medium channel with parallel flanges, and Indian standard heavy channel, or sorry, Indian standard gate channel. Indian standard gate channel. So these are the 5 types of channel sections we are having. Okay, and which is not that much important, just to know that there are 5 types of channel sections we are having. What is the meaning of MC? Means medium channel, MCP means parallel flange. What is the meaning of parallel flanges? If you have this kind of channel section, one flange is parallel to another. What is the meaning of sloping flanges? When you have this kind of thing, sloping, this kind of thing, sloping flanges, slopes are there for the flanges. These are called as MCP means Indian standard medium channel with sloping flanges. MCP means Indian standard medium channel with parallel flanges. Okay, I hope you understand this. Okay. Now let's move on to next, angle section. So what is the angle section basically? Where we are going to use angle sections? What are the advantages of angle sections? Okay, let us see one by one. So angle sections. So let us start that. Angle sections. So angle section is of 2 types basically. There are 2 types of channels angle sections we are having. One is the equal angle section, that is equal angle section, and the second one is unequal angle section, and the second one is unequal angle section. So what is the equal angle? Very simple in terms of understanding of this. If both the leg widths are same, so this is what one leg width, this is the one leg, this is the another leg. If both leg widths are same, suppose if this is 100, let's say leg width is, and another leg width is also 100, let's say for example. If both the leg widths are same, it is a equal angle, and the thickness should be uniform throughout. Here it is same. If this is 6 mm, this must be 6 mm. Okay, you understand this? So thickness is uniform throughout the angle section. Okay, leg widths are same, then it is said to be equal angle. Suppose if leg widths are different, for example, if leg widths are, look at here, one leg width is this much and another leg width is this much. So understand, dear friends, if this is 100, whereas another leg is, let's say, 120, and the thickness is same, this is 6 mm and this is also 6 mm. So this is said to be unequal angle. So if leg widths are different, here it is 100, there it is 120. If leg widths are different, it is said to be unequal angle. If leg widths are same, it is said to be equal angle. Fine. These are the 2 types of angle sections we are having. My dear friends, you understand one more thing here. Where do you provide this kind of angle sections? Where do you provide them? That is also the question mark. Where do you provide this kind of angle sections? these angle sections are better performing things in case of axial forces. Whenever there is an axial force, these are the best sections we can provide. Angle sections are efficient to carry only axial force. But whenever the moment comes, bending moment or twisting moment comes, then it will not resist them actually. So please understand that this particular angle sections are only capable of resisting the axial force. So angle sections are efficient in resisting axial forces. Angle sections are efficient in resisting the axial forces. That means it may be compressive force, it may be tensile force. Fine? Okay. Now the question, they are unable to resist bending. Very important thing is angle sections cannot take the bending. So we never provide angle section as a flexural member. Please understand it. Now, which section is best? We have equal and unequal. Which is the best section in terms of axial load carrying capacity itself? What is the answer? Just think and answer this question. If you want to answer this question, you have to understand economy plays a vital role. Okay, very important thing. Anything you can provide without investment, if you don't think about investment, we can go for always best. What is the point of going for always best? If already something is giving you efficiency, appropriate criteria are satisfied by a small thing, you can go with that. Why you have to go for every time heavy things? That's what you have to understand first. So my dear friends, what I am trying to say here is, out of this equal and unequal angle section, which is most efficient tension member? So dear friends, you understand that unequal angle section is the best tension member, provided that when its longer leg is connected to the gusset plate. Okay, let me explain clearly once again this, you have to understand this properly. So have you seen gusset plate first? What is the gusset plate? See, dear students, we cannot find any steel structure without gusset plate. So there must be a gusset plate. Always understand, remember this, there must be a gusset plate in any steel structure you take it. What is a gusset plate? Let me explain about what is a gusset plate. Okay, so I'll take another slide and I'll explain what is a gusset plate. So dear students, if you have, let's say for example, okay, so I want to construct a big truss. So let's say this is the truss. I want to join, okay, this is the one element of truss. This is the one element of truss and this is the another element of truss. Okay. Okay, and this is another element of truss. Okay, fine. So I want to join, see, listen, I want to make it as a triangular configuration. So all these are element pieces, simple pieces, single pieces. So to form a triangular network, you know, what is the truss? Truss is nothing but triangular network of tension or compression members, axially force carrying members. My dear friends, understand here that what is a gusset plate? See, to join two members, to join one or more members to another member, we require a gusset plate. See, that is how it is beneficial to us. See, if you want to join these two members, the width available may be less. What you do is you take one gusset plate, this is the gusset plate, yellow color one is the gusset plate. Then do welding of this one, bolting of this one with this one, this one with this one. This plate is connecting. Then connection is achieved between them. Are you getting the point? Gusset plate is that. So gusset plate is a plate, steel plate, nothing but a steel plate, simply a steel plate, which is used to join two members or more members to the another member. That is what we call gusset plate. See, that's all. Even if I want to join these two, just very simple, take a gusset plate, do bolting of this, do bolting of this, that's all. Here also same thing. This is the gusset plate, do the bolts here, insert the bolts here, insert the bolts, that's all. You will get the connection, yeah, that's all. Right? Now listen, suppose if I want to have one more, you want to have connection of something, I draw line diagram for better understanding purpose. Let's say there is a one tower already existing, for example, this is the tower. Now I want to, okay, see, look at here, this is the foundation of this, let's say some foundation is there, some foundation, okay. Now what I want to do is, I want to join a bracing member to this, see, look at here, this I want to create a bracing. So what I do for that is, first I take gusset plate and do welding to this one. Now I take another members from here and I connect to this. This is how I can make the connections. Is it clear to everyone? That's all. This is what we call basically gusset plate. That yellow one, whatever you see there, is the gusset plate. So what is the gusset plate? Gusset plate is a steel plate which is provided in the connection to join one or more members to the existing member. That's the need of the gusset plate. I hope it is clear to everyone. Now look at here. I want to apply maximum tension. See here, maximum compression as well. Suppose I want to carry more tension in this element, inclined element, I want to apply more force. When I want to apply more force it has to carry. And if I provide an angle section as this element, what is this element, ma'am? This element is a angle section. Angle section is having two legs. My hand, see, this is how angle section is. This is the one leg, this is another leg. I have to connect any one of the leg to the gusset plate. Any leg only I have to connect to the gusset plate, not two legs. If one leg is connected, another leg is like this. So now listen, which leg I have to connect to the gusset plate? That is the question mark. Dear students, go back. We have two angles, equal and unequal. Which is having more area? One leg. Which is having highest one leg area? Is 100 into 6 is higher area or 120 into 6 is higher area? 120 into 6 is the higher area. Is it clear? Yes. Now listen. When you provide a longer leg area to the gusset plate, then more force will be transferred to the connection. It can take more force. It can transfer more force. Are you getting my point? It's a very simple thing you have to understand. So whenever I want to improve my efficiency of axial forces member, provide larger area in the connection. Provide larger connecting member in the connection so that it can transfer more force. Is it clear? Right. Okay. If you provide least sectional area to the member, it will take only least force. What is the best one? The best one is the one which carries the heavy force. Best one is the section which carries the heavy force, heavy capacity. That is said to be the best one. Is it clear? Yes. Now understand, my dear friends. So to transfer the axial force, here also even, if this is the axial member, one leg is connected, another leg is outstanding. Which you provide as a connecting member? Provide larger leg as the connecting member and the shorter leg as the outstanding member. So only force is transferred to the connecting member. Please understand, in angle section especially, my dear friends, I will write here so that you can understand easily. So if I have, this is the gusset plate, let's say, this is the gusset plate, and let's say this is the angle member. This is the angle member. This is the angle member. We have two things. One is the shorter leg, another one is the longer leg. This is the shorter leg. This is 80, let's say. Let's say this is 120. This is 120. My dear friends, when I apply force on the angle, see, this is the gusset plate. Yellow one is the gusset plate. When I apply force on the angle member, which is transferring force to the another member, this is through the gusset plate. This is through the gusset plate. Okay, always remember whenever you apply force angle member, force is transferred to gusset plate through the connected leg. So always ensure that connected leg should be a stronger leg. This is the connected leg. The connected leg should be a stronger leg, and outstanding leg can be weaker leg, because outstanding leg purpose is only to give support to the connected leg. Majority of the load is transferred to gusset plate through the connected leg. Okay, if it is a plate, no problem. Plate means only plate. There is no outstanding leg, unconnected leg like that. But in angle section, we have two legs. This is the one leg, this is the another leg. One should be connected, another should be a outstanding or unconnected leg. So to transfer force effectively, do you connect 80 mm leg to the gusset plate or 120 mm leg to the gusset plate? 120 mm, because 120 mm leg is having more area than the 80 mm leg. When you connect more area member to this, we can transfer more force. That is the best section. So the best tension member is unequal angle section, provided that when its longer leg is connected to the gusset plate. When its longer leg is connected to the, this yellow one is the gusset plate. Okay, is it clear to everyone? This is the white one is the angle section. This white section is the angle section. In angle section, we have two legs. One is the connected leg. This is called as the unconnected leg. Unconnected, or it is also called as outstanding leg. Okay. So very important point which you have to understand. Make a note that the most efficient tension, the efficient tension member is the efficient tension member is the unequal angle section. Unequal angle section when its longer leg is connected to the gusset plate. Okay, please understand this. The efficient tension member is the unequal angle section when its longer leg is connected to the gusset plate. Please understand this. If you connect shorter leg, it becomes inefficient member. Please understand that. That's why in case of plate girders, to connect flanges with the web, we generally prefer the unequal angle section is connected to the flange, so that it can give more support to the flanges. I'll explain that in the plate girders. Don't worry about it. So then how do you designate angle sections? So angle sections are designated like this. Very simple. Like I am writing here itself, ISA. For example, if you want to designate ISA, you have to mention the shorter leg, then longer leg, then thickness. So but here both the legs are same, that's why it is equal angle. You can represent 100 by 6. Now coming to unequal angle section, this also we can represent. ISA means Indian Standard Angle Section. Longer leg multiplied by shorter leg multiplied by the thickness. So this is how we represent the unequal angle section. This is how we represent the equal angle section. Okay, clear to everyone? Longer leg into shorter leg into thickness. This is how angle sections are designated or represented. Clear to everyone? That's it. Always remember, gusset plate is compulsory. So this is what, any structure you take it, we generally have gusset plate in it. Without gusset plate, we cannot find any steel structures. That is the very important thing you have to understand. So gusset plates are essential to transfer loads from two members to the another member, etc. Right? That is what you have to understand. Now comes the another one, what we call as T section. So very simple thing. What is the T section? So T sections are the least number of sections we are getting from Indian rolling mills. So these are the least number of sections which are fabricated from Indian rolling mills. Why T sections are less in number which are producing from Indian rolling mills? There is a reason behind it. What is the reason behind it? Very simple. if I want to get T section, for example, this is the T section, look at here carefully. This is the T section, let's say. If this T section I want to get, how to get this T section? Very simple thing is that 2 angle sections, that's all. You take one angle section, this is the one angle section I am having. This is the one angle section I am having. Take another angle section also and connect 2 angle sections back to back. Then you get the T section, that's all. So 2 angles, 2 angle sections connected back to back will give you T section. That's all. That's why very least number of T sections we are getting from Indian rolling mills. So this is not having much significance. Then where do you provide this kind of T sections? So T sections are generally provided for overhang connections. What connections? Look at here, we have a slab. This is the slab we are having, let's say. So this is the slab. To the slab, we are attaching some bolts. Let's say some bolts are attached. And it's overhanged from that, and something is attached to this. Let's say some weight is actually overhanged from this. This is the weight we are having, which is attached to this T section. Okay, and this particular weight is going to pull down. So there is a tension developed in the elements. So this is what exactly is happening. So there is a tension developed in the bolts. Here also there is a tension. So in overhang connections, whenever you apply force, certain weight is applied to this. There is a connection here also. There is a connection between them. Some kind of arrangement is made and the weight is connected to this. So then what happens is this weight, whatever is pulling down, is going to cause tension in the bolts. Then bolts are undergoing the tension here. That is what exactly happening over here. Okay, so overhang connections we use the T sections. So T sections are used for overhang connections, and these are also provided as stiffeners some cases, water tanks, etc. There is no other much significance of these T sections when compared to the other sections. Now comes the very important thing. Okay. Hollow sections. What sections? Hollow. What are the significance of hollow sections? Let us look at that. So hollow sections. What are the hollow sections? How many types of hollow sections are there? Let us look at that. So hollow sections are of 3 types. What are those hollow sections? Let us look at that. One is the rectangular hollow sections. The second one is square hollow sections. The third one is circular hollow section. So rectangular hollow section, let's say this is what rectangular hollow section. See, this is what it is. This is how it is. So this is the rectangular hollow section is. So we have material only on the periphery. We have material only on the periphery like this. And we have square hollow section. This is the square hollow section is. This is the square hollow section is. So we have XX, this is the ZZ axis, this is the YY axis, even this also ZZ axis, and this is the YY axis. This is the rectangle, this is the square, and we have even circular hollow section. This is what it is, this is how it is. This is the circular hollow section. Here also material is there only on the periphery, that's why it are called as hollow sections basically. So this is what ZZ, and this is the Y, circular hollow section, rectangular hollow section, square hollow sections. If you observe carefully here, that we have center of gravity. This is the center of gravity and shear center both coincides. In any hollow section you take it, both center of gravity and shear center coincides. You take any hollow section, this is happening because hollow sections are symmetrical about both the sections, both the axes. So I can say that here hollow sections are symmetrical about both the axes. Hollow sections are symmetrical about both the axes. Both axes. If hollow sections are symmetrical about both the axes, then center of gravity and shear center coincides. Center of gravity and shear center coincides. There will not be any torsion developed in these sections. That's a very important thing. One more advantage of hollow sections you understand clearly. In hollow sections, material is located or thrown far away from the axis. You take this section, this axis, material is located far away. There is no material nearby. This entire thing is hollow. In hollow sections, material is thrown far away from the axis. If the material is thrown far away from the axis, you know, moment of inertia increases. You might have learned this in engineering mechanics. I is equal to AR square. If a metal is located far away from the axis, moment of inertia is also increases. Please understand, material distribution plays also vital role. So more radial distance you spread the material, more will be the moment of inertia. Less radial distance you spread the material, less will be the moment of inertia. So please try to understand that. Now my dear friends, in hollow sections, because material is spread far away from both the axes, there is a more moment of inertia about both the axes. So what I can say here is that, so hollow sections have almost equal moment of inertia about both the axes, IZZ and IY, because symmetrical. Little bit variation is there in this rectangle, but square and circular having same moment of inertia about ZZ axis as well as YY axis. And not only that, but individual moment of inertia is also more. Very simple. IZZ is more because R is more. Even IYY is also more because R is more. So, which means that individual moment of inertias are more. At the same time, moment of inertia about ZZ and YY also same. Highest moment of inertia is possible in hollow sections. Very, very important point you have to understand. Highest possible moment of inertia is there only in hollow sections. So hollow sections are having large moment of inertia. Please understand that. Hollow sections have, I can say here that hollow sections have a larger moment of inertia. MOA means moment of inertia. Therefore, and almost they have larger moment of inertia, and also we have to understand, and comparable moment of inertia. Comparable moment of inertia about both the axes. Both the axes. Comparable moment of inertia about both the axes. Therefore, polar moment of inertia is more. Therefore, polar moment of inertia J or IP, J or IP, which is equal to IZZ plus IYY. IZZ plus IYY. So, individual moment of inertias are more. Therefore, polar moment of inertia is also more. Therefore, I can say hollow sections are, therefore, hollow sections are most efficient. Hollow sections are most efficient sections. Hollow sections are most efficient sections to resist torsion. Among all the sections, hollow sections are the most efficient sections to resist the torsion because their individual moment of inertias are more. Because their individual moment of inertias are more, therefore polar moment of inertia is more. If polar moment of inertia is more, you take the torsion equation T by J is equal to tau by R. So from this we can say the torsion capacity is equal to tau by r into z. Because hollow sections are having more polar moment of inertia, they can resist more torsion. They can resist more torsion. Is it clear to everyone? More polar moment of inertia, more torsion it resists. It is clear to every one of you, I guess. So the important conclusion is, whenever they ask this kind of questions in the exam, which of the following is the most efficient section to resist the torsion? The correct answer is hollow sections are the most efficient sections to resist the torsion.